Okay, a very good morning to all of you. So far, we have discussed estimation of a number of physical properties of celestial objects. Namely, we discussed about luminosity, we have discussed about brightness, we have discussed about mass. And in this presentation, we'll discuss about measurements of sizes of celestial objects. We will discuss a little bit about spectra while discussing stars as well as galaxies. But this presentation will confine to measurements of sizes of celestial objects. So for example, a well-resolved source like the sun, for example, which is relatively close by, once you know the distance to the source and you know the angular dimensions, then you can straight away measure the linear size of the object or a part of an object. For example, in this particular image of the sun, you can see that the most dominant feature has been quite a large dark coronal hole at the bottom of the sun. Coronal hole areas are areas where the sun's magnetic field is open-ended and where high-speed solar wind streams out into space. And this is what is responsible for the space weather, for which a lot of effort has been spent in recent times in studying it. The area appears darker there because there's less material being imaged in the wavelength of extreme ultraviolet. And it is pretty big. At its widest point, the hole extends to more than 50 times the size of the Earth. So as you all know, the sun's surface is a very active surface, and a degree of activity varies with the solar cycle, which is estimated by the number of sunspots that you see on the solar surface. So for example, this object you can see can be easily measured because you know the distance to the sun. You can measure the angular dimensions of what you're observing, whether it be the entire size of the sun or a particular region of the sun, as in this case, it is the coronal hole. Okay. Now, but it gets more difficult measuring the sizes of stars when they are further away. For example, here what I have done is I've just taken the sun as an example, which, as you know, subtends about half a degree, which is about 30 arc minutes or so, at a distance of 1 astronomical unit. Now you can ask yourself the question, what would be the angular size of the sun if it was placed at a distance of 10 parsec? You'll remember from our discussion of apparent and absolute magnitudes, that an absolute magnitude is defined as the magnitude of a star or an object which it would have at a distance of 10 parsecs. And you recall that 1 parsec is 206.265 astronomical units, or roughly about 3.26 light years. So I've done a simple estimate of what the angular size of our sun would be when it is put at a distance of 10 parsecs. And you can see over here that it is a minuscule amount. It's 0.93 milliarc seconds. So even the Hubble Space Telescope, even spaceborne telescopes, would not be able to resolve this object. So that remains a challenge in determining the angular sizes or diameters of stars. But we will see in a little while how we can overcome these limitations and at least extend the distances to which stellar diameters can be measured. But on the other hand, if we have large objects, for example, this is a double-lobed radio galaxy, Cygnus A, one of the early radio galaxies to be identified. And as you will recall, it is one of the more luminous radio galaxies, identified by hotspots or bright regions at the outer edges of the lobes of radio emission. The nucleus over here, which you see lies at the nucleus of the host optical galaxy, which is not seen in this image. And from the nucleus of this host galaxy, which hosts a supermassive black hole, jets squirt out at relativistic velocities to first the interstellar medium and then the intergalactic or medium, and forms these bright regions of hotspots, which are the termination regions where the hotspots interact with the external medium. Here, there is not much of an issue in trying to measure the angular dimensions because this can be easily measured from end to end of the hotspots. And once you know the angular dimensions and you know the distance to the object, then you can find out what the linear dimensions are. Because galaxies are at cosmological distances, that you have to use the correct cosmological parameters in estimating the distance to the object. As you will recall, this is what we discussed while discussing the various rungs of the cosmic distance ladder. I've just given over here what the scale of conversion would be at redshifts of 0.5 and 2.0. Okay, and the angular diameter distances. The angular diameter distance is what you will have to use while trying to estimate the linear dimensions of extragalactic objects. And the luminosity distance is what you would use if you were estimating the luminosity of the object from the observed flux density. dA and dL are related by 1 plus z squared. And this is something which you will learn when you learn cosmology later on, not as part of this course, but in future courses. And this gives you the scale factor of what 1 arcsecond corresponds to how many kiloparsecs. And there is a very useful Java tool which Ned Wright has put in the web. I've given the link over here, and you can play around with different redshifts, different angular sizes, and try and make some estimates yourself. Now, in the case of the radio galaxy Cygnus A, the end spots were very well defined. But when I look at the galaxy, it sort of slowly fades away into the general intergalactic medium. The intensity decreases and ultimately merges with the general intergalactic medium. There is no sharp boundary. It is not like a rod. So how does one measure the sizes of these objects? So what one does is one tries to define a brightest limit to which you would measure the dimensions of the galaxy. Holmberg defined a radius till a brightness limit of about 26.5 magnitude per arcsecond squared in blue light. You'll realize that this may also depend on the wavelength at which you're observing. We saw that when you look at neutral atomic hydrogen, that could encompass much larger than what you see at optical wavelengths. But right now we're talking about the sizes of galaxies, say in the optical region of the spectrum. The fainter you go, the boundaries are less well-defined and they're more prone to errors. So there is also tendency by several astronomers to define it to about, say, 25 magnitude per arcsecond squared, whereas Holmberg has gone a little deeper. Here you can see two kinds of galaxies. One is a dusty spiral galaxy and the other is an elliptical galaxy. And we'll learn a lot more about galaxies later on, but these galaxies are classified just according to the shapes that they occur to you. How they evolve, how they form is an interesting story as well, which we will try to touch upon later. Now, for stars, from a theoretical perspective, you can try and estimate what the sizes are likely to be. That comes from the fact that the stars radiate approximately like black bodies. And so you can use the Stefan Boltzmann's law that the luminosity of a black body is equal to 4 pi r squared sigma t to the power of 4, right? Where r is the radius of the object and t is the temperature of the object. In this case, we're talking about a star. And if you know the observed flux of the star, and you know the distance to the star, then you can get the luminosity of the object. And from the Wien's displacement law, from a look at the black body spectrum where it peaks, you can get a measure of the temperature of the star. So this will give you an estimate of the radius of the star because sigma is a constant, L and T are known, so the only unknown is the radius. So you can use this theoretically to try and get an estimate of what the radius of the star is. But can you observationally measure it? That is the challenge, right? Challenge in measuring the diameters of stars. And one of the techniques which was discovered, which was to try and make high resolution images, because clearly when the angular sizes are small, that you need observations of high angular resolution to be able to measure the sizes of these objects. And we just saw that even at a very modest distance of 10 parsec, that our sun goes down to about 0.93 milliarcseconds. And when you observe from the Earth, the turbulence in the atmosphere blurs the images because the atmosphere, the turbulence cells in the atmosphere keep moving and your image keeps moving as well. And so one of the things which was done, which was attempted and which seems very successful in trying to get higher angular resolution, is to make observations with very small time scales, or the order of 10 milliseconds or so at millisecond sort of time scales. How small, that would depend on the wavelength that you're operating at as well. But basically, for that small time scale, you want the atmosphere to be almost stationary. but it is going to move 10 milliseconds later, or whatever millisecond time scale, depending upon the wavelength that is relevant. Now, so what you will get for a single object like a star, you'll get a lot of small dots in your recording device, whether it be a CCD or a photographic film. And what you need to do is reconstruct the image from these speckles. So this is just an example over here. Okay, example over here, where there is a binary system over here. But you can see when you look at it at small, very small time scales, you can see a lot of dots where it has been scattered out. But you can see the two main peaks as well, where most of the emission is. Whereas if you were looking at it with just a ground-based telescope, seeing would actually give you a slightly elongated image because there are two stars over there. But you can see from a speckle reconstruction that you can see two images quite clearly. Okay, so this is one technique of trying to get high angular resolution. Okay, but the resolution is limited by the diffraction pattern. We talked about diffraction and the seeing and the Rayleigh criterion for the resolution that you would get with a telescope of a certain size, whether it's a mirror in the case of an optical telescope, or whether it's an antenna in the case of a radio telescope, right? And that is given by 1.22 lambda by d, which is basically the radius of the central airy disk over here. Okay, and this is related to the Bessel function Jn, but all you need to remember is that this is 1.22 lambda by d, where lambda is a wavelength of observation and d is the diameter of the mirror or the aperture that you're looking at it. You'll recall that the peak of one PSF lies in the first minimum of the other, and that is what gives you 1.22 lambda by d, the separation. Shorter the wavelength, the better the resolution. Or higher the size of the mirror, the better the resolution. But on the other hand, there would be a limitation to seeing, but that is to a certain degree overcome by not only speckle imaging, but also techniques such as adaptive optics and active optics, where you sense the corrugation in the wavefront and try to adjust your mirror to get as close as possible to diffraction limited images. You can also go outside the atmosphere, as the Hubble Space Telescope has done, to get rid of the effects of the atmosphere in terms of blurring the images. But any hope of direct imaging of a star to get R, the radius of the star? The answer is yes. The answer is yes, but it has to be a pretty massive star. Its linear dimensions, intrinsic size dimensions has to be very large. And this has been done, for example, what I've shown you here is Betelgeuse. The red giant star, which you can see in the constellation Orion, is a bright supergiant. And you can see by a comparison of the radius of the star or the size of the star with the size of Jupiter's orbit. You can see it is larger than Jupiter's orbit. So it will engulf the entire solar system till about Jupiter. Saturn just sort of lies a bit beyond it in this visible ultraviolet region of the image of the star. And the optical interferometer methods give a size of 54 milliarc seconds. But we will come to interferometry as well. But if you had images which were not limited by seeing, but were limited by diffraction, then ideally you could go and measure directly the sizes of some of the giant stars, which should also be relatively close by, so that the angular size it subtends is much greater than the diffraction limit from the Rayleigh criterion. Here is just to show you the point spread functions of what Betelgeuse looks like compared to another point-like star, which is much smaller. And Betelgeuse has actually a slightly higher size at the ultraviolet wavelengths compared to the optical, is higher opacity of the chromosphere, increases the apparent size. And this is an image which was taken with the Hubble Space Telescope. And as you go to shorter wavelengths, your resolution also improves, it gets better. And the UV diameter is about 125 plus or minus 5 milliarc seconds. And this image, as I showed on the bottom right, is to compare the broadening of the Betelgeuse profile with another sort of point-like star, HZ4, and you can clearly see that Betelgeuse is well resolved in these observations, and you can go and infer what the angular dimensions are. And once you know the distance to Betelgeuse, then you can go and find out what the size or intrinsic size in terms of astronomical units or meters or kilometers, what the intrinsic size of Betelgeuse is. Betelgeuse, you remember, is a pretty big star. It's a giant star. It's a red giant star. The other technique which has been used and which is a very clever technique is to resort to diffraction. When a point source goes behind a straight edge, you're familiar from optics with the diffraction pattern that it will cause. Now, you can use the moon as a straight edge diffracting edge. And if a source gets occulted by the moon, then you will see a diffraction pattern with your telescope. And this is a technique which can be used not only at optical wavelengths, but also at other wavelengths. For example, at radio wavelengths. In fact, the UT radio telescope, which we discussed when we talked about the radio window of the electromagnetic spectrum and radio observations, that it follows the moon. It follows the moon to measure the angular sizes of compact radio sources. And looking at the diffraction pattern, you will be able to infer the size of the compact radio source. In fact, because radio frequencies are large, you really need very long baselines to get even a fraction of an arc-second resolution, lambda by d. Okay, lambda is very large. But by resorting to this technique at low frequencies, it was at that time the best known technique to infer the angular sizes of radio sources. Today, we have actually gone a lot further. We have built very good interferometers at low frequencies, whether it be LOFAR in the Netherlands, GMRT in India, to achieve high angular resolution at low frequencies as well. In fact, LOFAR has antennas spread across the European continent and is achieving very high angular resolution at low frequencies, better than anywhere else right now. And for the stellar diameters, what we can do again is use the same method, that the edge of the moon, which is a straight edge, gives rise to a diffraction pattern as the star gets occulted by the moon. And the figure over here shows that shows the change in the diffraction pattern as the angular size of the star changes. You can see when it is very compact, it's 0.0027 arc seconds, and it keeps increasing to 0.005 arc seconds. Then it comes to 0.0099 arc seconds, and it comes to 0.0413 arc seconds. And then when it sort of becomes very broad, you will not see the diffraction pattern. Okay, so by working backwards from the diffraction pattern by deconvolution algorithms, you can go and infer what the angular size of the star is. And once you know the distance, then you can also determine what the linear dimensions are. The only drawback over here is that the moon will follow its path. You can't tell the moon that I'm interested in that source, so go there. So you'll have to be satisfied with what gets occulted by the moon as it moves around the Earth and as the Earth moves around the sun. I just want to illustrate to you again over here that the time scales over which you need to make the observations are quite small. You can see that one full orbit around the Earth that's 360 degrees. It does in one lunar sidereal month, which is about 27.3 days, 27 days, 7 hours roughly. So if you work it out, and you can check my sums to make sure I've done it correctly, it's about 0.55 arc second per second. So if it's a 100 milliarc second star, it'll go through in a fraction of a second. Okay, so you'll have to be you'll have to have good timing devices to try and record the signals with very small time resolutions. Okay, and the Archery group, which has specialized in lunar occultation measurements, this is from this figure which I've shown you is from that group. They have measured stellar sizes to about milliarc second levels. So this is a good sort of way or method of determining angular sizes, and then from the distance to the linear sizes as well of stellar objects. I'm focusing a bit more on stellar objects because they are the most compact objects and it is a challenge to try and measure the sizes of stars. Now, the other method, which I'm going to talk about right now, is when stars are in a binary system, particularly when they are in an eclipsing binary system. Okay, here I will be making a number of simplifying assumptions. I will assume that the inclination angle is 90 degrees. Okay, so actually I'm seeing this edgeways as the smaller star. The smaller star, by the way, over here is actually the hottest star. I've taken this discussion from Karen and Osley, so you can follow this in more detail. It's on the chapter on binary stars in that book. Okay. Now, the smaller star is orbiting around the larger star, and the smaller star is the one which has a high temperature and is more luminous. Now, you can see from here that just by assuming a circular orbit, I can write down the velocity of the stars as 2 pi a1, which is by p, which is the period. Okay. This is nothing but v is equal to r omega, which you're familiar with from a very basic physics. So omega would be 2 pi nu, and nu is 1 upon p over here. Right. Now they're both rotating about the center of mass of the system. Okay, as you saw in our discussion of estimation of masses, that a binary stellar system would both be rotating about the center of mass of the system, just as in our planetary system as well. And then we can also write down the ratio, because these are both moving about the center of mass of the system. M1 upon M2 is equal to V2 upon V1, so that M1 V1 is equal to M2 V2. Now, for example, if I look at this stellar system over here, and the smaller star is going around the bigger star, you can see the various positions have been marked over here: A, B, C, D, E, F, G, H. So you can time it because from the light curve, this is nothing but the magnitude or the intensity or the flux, okay, as a function of time. So as it approaches, okay, the light is going to dim, right? Because light from one star is hidden by the light from the other star. Okay. Now, when both the stars are visible, then you'll get the maximum amount of light because you're adding up the light from both the stars. But once it starts going behind, you can see that TA is when it starts going behind. Okay. And by B, it is completely inside. So that is when it reaches the minimum. And as long as it is within the minimum in an eclipsing binary, this should remain flat, because there is no other extra light which is coming to your observer, and then it starts coming out. So at TC, it just starts coming out. Okay, it's just touching the edge, and then by the time it's D, it is completely out, and it goes back to the sum of the two stars. Okay, and similarly E, F, G, H, except that now E is over here, and then you're beginning to cut off light from the less luminous star. So that is why the dips are different, and then this continues to hide the light from the star till it reaches G, and then it begins to start coming out. So it'll go up again, and then you get this part of the light curve where you see light from both the stars. Okay. Now I can estimate the radius of these two stars. How do I do that? Just by timing, because you can see over here that from the timings of B and A, when it is over here to when it is gone completely eclipsed, that will give me the diameter of the smaller star. And to know the diameter of the smaller star, I have the timings, and I have RS, which is equal to velocity, because I have to know the velocity at which it is moving out, and I've divided because that is the diameter, and I want the radius. Okay. V is a relative velocity between the two stars S and L, because S is the smaller star, L is the larger star. And similarly for the larger star, you can go and determine what is the diameter of the largest star, and you can see you can determine it from the time when it is just entering to when it is just about to come out, because this is the length and that is the diameter of the bigger star. So I can write down RL is equal to V by 2. This is again because I'm interested in the radius over here, not the diameter. So factor of 2 comes in over here, TC minus TA. So which is a little bit of algebra. I can write down that the radius of the larger star is equal to radius of the smaller star plus V by 2 TC minus TB. Okay. And TC minus TB you can see over here, which is the timing of these two features over here. All right. So let's see now what we need to know, the velocity. Without knowing the velocity, we can't go and estimate the radius. So now let's go and see what we can do with that. So we have to determine the velocity spectroscopically. Because it's in a binary system, they're both moving about the center of mass of the system. So the spectral lines from the stars are going to shift, right? As they're moving about the center of mass of the system. So let's take this particular binary system as an example to illustrate how we go about it. This is a binary system with a period of 8.6 years. And the maximum Doppler shift delta lambda of the Balmer H alpha line is equal to delta S for the smaller star is 0.02 nanometers. And for the larger star is 0.0068 nanometers. Okay. Now you can see over here that H alpha line is what we're looking at, which is a line which is commonly observed in stars. And once I know by how much it has shifted, okay, that is related to the velocity. And you can see the shift is smaller for the larger star. And you can see over here that the ratio of the masses would be equal to the ratio of the velocities, which would be equal to the ratio of the shifts in the lines. And this is something which we had discussed while discussing binary stellar systems while we were trying to measure the masses of objects, right? So from the shifts in the lines, one can get a ratio of the masses. Okay? So in this particular example, we look at both how we estimate the mass along with the radii on this particular system. This example is again from Carroll and Osley, as I mentioned. So you can look it up in more detail. So we are going to just go by what Carroll and Osley has done over here. The velocity at which it is moving would be related to the wavelength by which the H alpha line is shifted. So we know we have been given by how much the H alpha line has shifted. So using just VRS is equal to delta lambda upon lambda into C, that will give me the velocity at which it is moving out. I put everything in kilometers per second. So the velocity of light over here is in kilometers per second. And over here, this doesn't really matter. It's in nanometers and it's a ratio. So as long as your units are consistent, it is fine. So this gives me a velocity at which the smaller object is moving is 32.9 kilometers per second. And the bigger object is moving at a lower velocity of 3.11 kilometers per second. And you can get that by doing exactly the same exercise. You can see the shift is much smaller, and that is why the velocity is also much smaller. Once you know the velocity at which it is moving, you can also find out what the semi-major axis is, AS for the smaller star, which is nothing but VRS P upon 2 pi, right? Okay, and then you can work that out and you will get the semi-major axis and of the smaller star. And by repeating that exercise for the larger star, you will get a value for the larger star as well. And you will recall that A, which comes into Kepler's equations, is the sum of AS plus AL for a binary system, right? Now, what do we have? We have estimated A because we have estimated AS and AL. We have been given the period of the star. So we have M1 plus MS. This is just applications of Kepler's laws, where the constant actually goes away. If M is in units of solar masses, P is in years, and A is in astronomical units, I can express this as M1 plus MS, ML plus MS equal to A cubed upon P squared. I've determined A, I've been given P. So I can go and estimate what the sum of the masses are, which will be in units of solar masses. And I already know what the ratio of masses are from the Doppler shifts of the lines, right? So from this, I can go and estimate what the masses of the two objects are. So this is an illustration also of how to estimate the masses of objects in a binary system. We discussed about masses in our earlier presentation, but here we are also interested in the radii of the stars, right? So we have gone so far. Now let's go a little bit ahead and try and go and get the radius of the star. Now we have got the sum of the two masses, which is 15.1 solar masses. We've got a ratio of the two masses, which is 10.59 solar masses. And clearly, once you have the sum and the ratios, you can easily work out, and you'll find the mass of the smaller star to be 1.3 and mass of the larger star to be 13.8 solar masses. So from that, now we come back to our timing observations. Okay, we know the velocities. This velocity is the sum of the relative velocities of the two objects. So RS is equal to, and from the timing, I'll know that V by 2 is equal to TB minus TA. This is what we had done earlier, okay? And because V is the relative velocity, so we add up the velocities VR plus VRL, which you determine from the spectral shifts of the lines, divided by 2 into TB minus TA, which we find from our timing, and then we can go and estimate what the radii of the stars are. And similarly, I've written down a similar expression for the radius of the larger star. And from the measurements which we have, say, we've been given that TB minus TA is 11.7 hours and TC minus TB is 164 days, okay? So this, this timing itself will tell you it's a pretty big star, right? So when we plug in these numbers, we get a radius of the smaller star, which is 1.1, our sun, and the larger star, which is 369 times the radius of the sun. And as you will recall, the radius of the sun is about 6.96 into 10 to the power of 8. Now, I mentioned about interferometry. The angular resolution is given by lambda by d, where d is the separation between the two apertures. Now, when we talked about a single mirror or a single antenna as in radio telescope or a resolution of our eye, we talk about the size of the receiving device. In the case of our eye, it's the pupil. In the case of a radio dish, it's the size of the antenna. In the case of an optical infrared telescope, it's the size of the mirror, because almost all telescopes are reflecting telescopes these days. And that is what D comes in. But when it comes to the interferometer, it is a separation between the furthest antennas that gives you the resolution. So you can see once D increases, your resolution increases. But the challenge is in trying to combine the signals. And with angular resolutions, with high angular resolutions, you can go and measure the radii of stars. You can measure better than what has been done with a single antenna. Now, there have been a number of interferometer telescopes at both optical and infrared wavelengths which have come up. And we will just mention that briefly over here. And the concept of actually combining signals is similar to the Michelson interferometer, which you would have studied as part of your undergraduate course. And this technique was used by Michelson and Pease way back in 1920s. In fact, they published a paper which reference I've given over here in the Astrophysical Journal, okay, where they measured the diameter of Betelgeuse as 47 milliarc seconds. The sizes of Betelgeuse is also very wavelength dependent, okay, as I mentioned earlier as well. And what they did was, on top of the telescope, they actually put up four mirrors so that the separation is larger and they get a better resolution. And that was one of the very early attempts in trying to get high angular resolutions. And John Baldwin at Cambridge, he pioneered that technique of putting masks and getting high angular resolutions as well. And but today we have a number of interferometers operating at optical and infrared wavelengths. The picture I've shown over here is a Navy precision optical interferometer near Flagstaff, this is in the United States. And that has actually revealed a lot about binary systems, about the motions of binary systems. And there is also majors, which is the Mizar binary system. The motions have been followed by interferometric observations, which I've shown over here. So interferometry is another important way of trying to measure sizes, okay? But I just want to mention one or two things extremely interesting about Betelgeuse. This is a determination of the size, okay? Alpha Orionis, Betelgeuse. over a 15-year period. You can see the 1983 November over here and 2009 over here. This was done by Charles Towns and his group, and it's using the same telescope at the same wavelength. Okay, so as I mentioned, that the size of Betelgeuse also depends on the wavelength. And so if you made it at different wavelengths, you will not be able to find out whether there are any systematic changes or not. But they have observed it at infrared wavelengths over with the infrared spatial interferometer, ISI, and measured it over a 15-year period, and Betelgeuse seemed to be shrinking. And shrinking on such a small time scale is something I'm not sure is completely well understood, but these are the kinds of observations which open up new frontiers of trying to understand even nearby stars, relatively nearby stars or large stars. Okay, and so resolution is extremely important, not only for measuring the sizes, but also for looking at finer scale structures in stars, as well as other objects. Here I've shown you the ALMA image of Betelgeuse. ALMA is the Atacama Large Millimeter Wave Array. And then you can see in the middle panel, the infrared observations, which has been done with the European Southern Observatories, a very large telescope, VLT. And the red circle, which you see in the middle panel, right over here where I'm pointing my cursor. So that is where the visible surface of Betelgeuse is. So you can see it's a huge star, but what we see in the optical or ultraviolet, and the infrared is actually even throwing out deep observations have shown much more material, and it is not even smooth, it is sort of not symmetric either. So these are important observations to learn about the physics of these objects. But in today's presentation or discussion, we'll just confine ourselves to the measurements of sizes of these objects. But there are exciting things happening even in this bright star in the Orion, which you can actually look up in the sky tonight and have a look. It's a bright star in the Orion constellation, which you can see. And Betelgeuse also seems to be dimming. This is January 2019 to December 2019. There is a decrease in brightness. This is also observations done with one of these telescopes. So this is a brief sort of introduction to the measurement of sizes of celestial objects. I put a lot more emphasis on the measurement of sizes of stars because that over there lies the greatest challenge. In terms of measuring sizes of other objects, for example, right in the nuclear regions of active galaxies, what is the size of the Schwarzschild radius, for example? So today we have the Event Horizon Telescope, which has achieved the highest angular resolutions possible by combining observations with telescopes all across the world to image the area around the black hole. So in terms of direct imaging, that this has been one of the highest resolutions which have been achieved at sort of millimeter wavelengths, and has opened up a new window of looking at the nuclear regions of active galactic nuclei and have a better understanding of that region and understand better the launching of radio jets, which is still an area which you don't completely understand, although there have been a lot of interesting suggestions and ideas and observational evidences as well. At X-ray wavelengths, as we saw, it is very difficult to get such high angular resolutions. But we try to infer sizes or size scales from time scales of variability. For example, we talked about that, for example, a certain region to vary coherently, the signal can travel at a maximum speed of light. So from time scales of variability, we can infer limits or estimates of the sizes of the regions which are varying by putting in the velocity of light and also incorporating possible relativistic effects, which are relevant when we talk about jets which are moving at highly relativistic velocities. So this lecture gives you an overview of sizes.